Hello and welcome. Thank you for joining us today for our webinar, How to Steal AI Algorithms on the Edge and Protect Them. I'm Dr. Arun Serafin, Executive Director of NDIA's Emerging Technologies Institute. ETI produces research and educational products that focus on defense, technology modernization, and innovation. Today we'll be hearing from a panel of experts about AI algorithms deployed in microelectronics. What are the risks for commercial and defense applications, and how best to protect algorithms from tampering threats? With microelectronics underpinning so many elements of emerging defense technologies, especially in edge environments, for example, the way drone warfare has shaped the war in Ukraine, it's hugely important to be aware of where vulnerabilities are and how to mitigate them. So, this is a very timely topic, and we have a great group of speakers convened today to share perspectives from across government and industry. With that, I want to thank Mercury Systems for sponsoring today's webinar and turn it over to our moderator, Mr. Tony Trin. Tony is Senior Director of Mercury Systems Advanced Concepts Groups. Thanks for joining us, Tony.
Yes, thank you, Arun. Appreciate the opportunity here to speak. Yep, and I'll be your moderator today on this topic, and really want to sort of dive into this topic and introduce our panel of experts that we have. But first, before we start there, can we just go to the next slide? So this is, in my mind, sort of the challenge that we have in front of us, right, is when we look at the tactical edge and sort of, what we mean by the tactical edge in this slide, kind of describing what that means, right? It's an area where you got an environment where compute resources are very limited, communications are intermittent, and decisions need to make very quickly, such as on a battlefield aboard drones or forward operating bases. So how does AI fit into this? So in the traditional sense, before AI came along, a lot of these decision making were sort of local to the actual platform itself. And the vision for the future is really to try to make these platforms start to communicate with each other and try to collect large amounts of sensor information and try to make turn the information into some sort of decision making, so that those that are deploying these capabilities can better engage threats and things like that. So that's how AI has sort of amassed itself to this particular area as far as deployment on the edge, and in particular sort of edge platforms. And a lot of these edge platforms are commercial in nature. Things like GPUs, CPUs, and ASICs are running AI inference algorithms at the edge, so that it can do computer vision, sensor fusion models, things like that, and be capable of making active decision making on the target rather than sending data back to the ground or sending data back to a battle center to make decisions, and actually making those things more organic onto itself. So as you can kind of imagine, a lot of these things, these algorithms, are very high valued assets now that could easily be lost on the battlefield or be easily lost to some of our adversaries that want to use it or try to glean information in terms of how we make decisions related to these systems. And so there's some examples there in the bottom of where some of these things are going to be deployed, and these are active areas that are being developed or in development, and also in fielding in the next couple of years. So this is a very big topic for us here at Mercury, given that we do a lot of mission critical edge processing in terms of hardware and a little bit of software, but mainly in hardware, and trying to make sure that we protect everything we can related to that. So, so as far as that background, I want to kind of jump into our panelists here that we have. We've got three panelists, excellent panelists in the field of microelectronics and hardware assurance. So the first panelist I want to give opportunity to is John Malott, who also comes from Mercury, is my colleague, and I'd like for him to introduce himself and sort of any opening remarks that he has.
Sure. Thank you, Tony. I'm John Malott. I'm a chief engineer for secure processing at Mercury Systems. I think Tony did a great example of saying why this is a problem. And this is not just a defense problem. This exists in the commercial space too, with the same kind of considerations. And while the detailed motivations may vary, the threat model really is fundamentally pretty similar in those cases. And in fact, in some ways, somewhat harder in that, many commercial and industrial applications are much more widely proliferated than a defense application may be. So, I think there are lessons for both commercial and the defense space to be taken from this discussion.
Yeah, thank you, John. The second panelist I have is Dr. Wayne Sherman from the Army Research Laboratory. And Wayne, if you can give a quick intro.
Hey, Tony, thanks. I appreciate the opportunity to participate in this panel. Yeah, I've been at ARL for the last 20 years. My background started in MEMS and sensor design. But over the last decade, I've been pretty well embedded with the anti-tamper community, thinking about how we protect a lot of our forward deployed platforms from overrun scenarios or things where our platforms are going to get left behind. My current role is actually supporting the microelectronics commons. So I'm serving as the commons technical execution area lead for secure edge Internet of Things. And so the microelectronics commons is an ecosystem of 8 national hubs. And so I currently manage a portfolio of 3 of those 8 hubs and overseeing projects in several areas. So specifically looking at secure processors, encryption in memory, looking at secure waveform generators, and one particular project on secure GPUs. So looking at how we sort of push the needle on developing state-of-the-art lab to fab technologies to, again, enable us to perform more rapidly and be more agile at the edge. So definitely look forward to the conversations today. Thanks, Tony.
And lastly, but not least, Dr. Will Zortman from Sandia National Labs.
Hi, Tony. Thanks. And thanks to Mercury NDIA for putting this on. I know Tony and John and Wayne from years doing this type of work in the anti-tamper community. It's a challenging job protecting algorithms when you no longer have control of the system and the adversary has at least some access to the system. So I did that for a number of years with these guys, and now I lead a digital assurance for high consequence systems mission campaign at Sandia. That's a research campaign, and that's all about security as well. And it's about making trade-offs, evaluating threats, evaluating vulnerabilities as a consequence, so that you can actually rank risks and make trade-offs against different things, which certainly applies in this space. There are an awful lot of threats. There's a limited number of resources, and so you have to prioritize where you're going to put your energy, put your resources in order to meet those threats. Thanks, Tony.
Yep, thank you. So I've got some questions for you guys, just sort of on this topic, and we'll kind of go round robin, starting with John. The way I introduced you guys, John to Wayne to Will. So my first question, I kind of went through, why AI, but to you guys, each individually, why do you guys think that deployment of AI algorithms is happening for edge applications? Why do you guys think that that's the case? And if you can kind of go into a little bit of detail of what your perspectives are, that would be great.
Sure, yeah. Just to start, I think you hit on it in the introduction, right? It's about closing the loop on the chain from when information is gathered to when it's acted on. In the traditional model where, you take, in the case of a drone, right, you've got a person in a command center operating that drone remotely, right? And they may be able to see something and take an action based on what they see. But if they're in a contested signal environment, they may not have good connectivity. So it may not be a live thing. It may be something that they get after the fact. So the application of AI allows actions to be made autonomous in some cases. The other thing they can do for you is highlight areas of interest, right? And I can tell you, 30 years ago, I was working on a team that was working on enhancing mammograms to make them easier to read for radiologists, right? And it was really about, not so much giving you the final answer for every mammogram, which if you ever look at one, it's like looking at a snowstorm. It's about finding the areas of interest that are important for the radiologist to see. And so you can get some of those same benefits with AI processing.
Thank you. Wayne?
Yeah, so I think one of the we keep hearing this phrase a lot, especially within the DoD, that we have to be more agile, right? And we have to move faster, quicker. And I think that's what AI is enabling us to do, right? So there's an increasing demand for us to optimize systems that are, exhibit low latency, are more energy efficient. And of course, we're sort of limited by hardware resources when we're operating at the edge. So I think it's really important for us to be able to deploy these in our edge applications because we are relying more heavily on real-time information and being able to process that faster, right? So we think about our smartphones, but also sensors, drones, any type of networked scenario, right? I think the big thing that we're talking about within this community is convolutional neural networks, right? So being able to do object detection, facial recognition. But again, as we start processing more and more information, we have to worry about who has access to that information, right? And can our adversary use that information against us? So I think protecting the AI algorithms has become a more critical need, right? As we start trying to give our soldiers and our warfighters more situational awareness. Thanks, Tony.
Yep. Great answer. Thanks. Will?
Yeah, I think Wayne and John really touched on it. This is about being able to have our systems survive and operate in contested environments. So we've seen this in Ukraine. I think last week or this week, they captured a Russian squad using autonomous vehicles. I think those were remotely controlled, but when you're operating a non-contested environment and you're doing navigation, it's very easy. As soon as you cross over into a contested environment, whether you have to navigate or do other things, you may have intermittent or no connectivity with the system you want to control. And that's where AI algorithms come in, especially in navigation, which is something that we're focused on. That system has to be able to collect information from its environment, understand where it is so that it can navigate to where it's supposed to go.
And thank you guys for that. So my second question is so given that AI algorithms are so important and we got to protect them, what are some of the concerns with the lack of hardware assurance that may lead to things like tampering, reverse engineering, or theft of these algorithms? I'll start with John.
Sure. Well, I think of hardware assurance. The first thing I'm really thinking of, as a manufacturer of hardware, is that supply chain, right? Where are the materials coming from? How we as a manufacturer assure that those are what they're supposed to be. They're not counterfeit. They're not otherwise modified or in a way that's counter to the objective for the mission these are going into, right? And supply chain assurance. I mean, this has been around for a long time. It's a problem, and I think we see that it continues to be a problem. Because if you don't have a good hardware platform, if you don't have a known good system to start with, everything you put on top of that is at risk, right? If you were to have a counterfeit device that has a backdoor in it, for example, that's a great example of something that could potentially provide an opportunity to tamper or to reverse engineer something that might not otherwise, have that opportunity. So, those are some of the key things. And then that assurance then flows downstream, because when we deliver a product to our customers, how they handle it and how they use it is also part of this. And at any point in the whole chain, not having an understanding of where it comes from, that traceability through its entire life cycle, means that there are opportunities in supply chain for things to happen.
Yeah, absolutely agree. Yep. What about you, Wayne?
Yeah, no, I echo a lot of what John said. I think the biggest concern is really compromise to safety and confidentiality of the algorithms that are sitting on these hardware platforms, right? We talk about tampering, and yeah, that's the biggest thing, right? Tampering and sort of reverse engineering. If we, are putting our A list AI algorithms, right? Our biggest threat is that our adversary will be able to tamper with the models and reverse engineer the models and use it against us, right? Or potentially steal the IP, and then again we lose our competitive edge in theater. So I think thinking about how the adversary is able to take the models, manipulate the information, use it against us, or even exfiltrate information from the AI models. I think those are the major concerns. And I think it really all boils down to what is the cost of that compromise, right? And I think it's primarily safety and then the loss of our competitive edge on the battlefield.
Excellent. And lastly, Will?
Yeah, I mean, Wayne kind of hit on this. This is when you're talking about supply chain and assurance of AI models, I don't think a lot of people, I think people think about it. I don't know how much work has been done in assuring what these models actually are. There are ways to poison these models. These models put out a lot of information. If you're talking about commercial applications, they're learning off the internet. How much information on the internet is actually being generated by models, and how much self-poison, you're making copies of a copy, and essentially. And so I think there is a lot of concern about, at least from my perspective, concern about what is actually in the model. When you talk about the hardware and where the hardware comes from, we've talked about this in the assurance community for years. And that really, if you're talking about where these things are manufactured, I think that's less of a concern than it is with the design, potentially design tools, but also just well-meaning designers who may design RTL or software, things where the model is going to live, the kind of the support logic for those models being designed in a way that someone can exploit. And so when we talk about the kind of the supply chain and the assurance, my mind really goes to design, both to the design of the supporting logic and also the provenance of the AI algorithm itself.
So that's a good lead into my next question, which is like, how does one determine whether the product issues are due to quality issues or malicious attack vectors, right? How do you tell between one or the other? And are we always able to identify which has occurred? Are there some forensics that has to happen, right? For instance, us to determine if it's quality versus malicious. So I'm curious about what you guys' thoughts are. So I'll start with John on that.
Sure. Well, I mean, it's it's 6 of one, half dozen of the other to some extent, right? Whether it's a bug or it was a malicious insertion that someone put in there, the net effect is the same. And we certainly have got examples in the wild, in the commercial space of malicious insertions that have happened. There was a library that's used with SSH, for example. In the last couple of years, that was shown to have had some problematic logic inserted into it, right? And so that's happened, but every week there's a new CVE out with a really high score, it seems, right? So those things are actually a bigger worry into my mind. And how do you update and deal with that? And I think, as you consider that, kind of fundamental cyber consideration of, how you address newly discovered issues, right? You've got the same issue with your models. That you need to have a way of understanding if there are issues uncovered, how you're going to get updates and how you're going to fix that. And I think that's certainly an opportunity. And then looking at some of the work that's been done in the academic community on in terms of attacking AI models, I think there is an opportunity space there that's not well understood. Right, there's a lot of work that goes into maybe creating a model for a particular application and demonstrating it works, but demonstrating it's resistant to adversarial effects is not something that we really understand how to do in a systematic way. I saw a demo at an academic conference just 6 months ago, where on an ADAS system, a self-driving vehicle kind of application, someone was able, with a pulsed laser shining at a camera, to induce effects that would cause the vehicle to, say, turn in a controlled way. I mean, literally taking over the operation of the vehicle by what it was feeding into the inputs to the AI system. So, I think that's one big opportunity in terms of the assurance of AI algorithms. How do we, understand how to understand the impact or potential methods that might be used to by an adversary to induce effects. And obviously, if the adversary has access to the model, to the weights, and that's where the real IP is. It's in the weights that go into these models. Then that gives them a real leg up in terms of developing those sorts of attacks.
Yep, absolutely agree. And over to you, Wayne, about your thoughts on this question.
Yeah, no, so I think this is a tricky, problem to determine whether it's quality versus attack. I think ultimately you're going to have to do some sort of forensics to sort of decipher which one it is, right? I mean, you could just kind of take some common steps and just look at sort of the symptoms and the behaviors behind it, right? Because it could be something as, a known bug or something that's, triggering your system to crash or causing issues with the model. Or it could be, something as, more like a malicious reverse engineering attack. So I think until you actually have the hardware and you're looking at sort of its modalities and how it's operating, it's hard to determine if it's a quality thing or a malicious attack. But I think especially from the AT perspective, there's particular signs that you can look for, right, from a forensics point of view, that can sort of hint to, hey, these are more malicious in nature. Probably can't go into a lot of those things, but there's things that we know to be aware of, right, to determine malicious versus bad quality. So I think you just have to look at multiple signs, I think, to really draw a conclusion.
Yep, absolutely agree. And I think it's almost like a failure analysis, almost to some respect, right? You have to kind of do a fishbone to really understand what occurred, and look for the most likely candidates. So yeah, and lastly, to Will, this same question.
Yeah, I mean, I guess after your algorithm's been stolen or your system's been compromised, you don't care whether it was what caused it. That's, you're dealing with this realized loss. We deal with radiation environments in a lot of our systems at Sandia. If it was a bit flip from a radiation hit or a bit flip from an attacker, if the result is the same and the mission fails, then the mission fails. So I need to understand all those things. I need to understand, and with digital systems, whether they're AI systems or not AI systems, they, from our perspective and being able to understand them, they essentially have infinite states. The crashes of the Boeing aircraft and I think it was Indonesia and Kenya, those were unpredicted states in that system that caused those airplanes to fly themselves into the ground. that's what caused that. And so being able to understand every state that your software can be in is really tough. And when you're talking about AI algorithms, which the purveyors of these algorithms don't, will admit that they don't understand exactly how they work. Being able to partition off states that you care about or sets of states that you care about is really important. And it's really important to have a model, even if your model doesn't include the thing that someone eventually is, the 0-day attack or whatever that's eventually going to compromise your system. When that does happen, at least if you have a model, you can learn from it and you can update that and you can include that in future systems.
Yeah, just to pile on that thought, I think there are opportunities to place guardrails around our AI system. So the AI system may be able to make decisions to do things, but there may be a potential for, say, a rules-based engine or something else behind it to say, what's allowed, what's not allowed, so that you can contain the result to desired behavior. And I think on the other side of it too, just to highlight, what Will was saying, one of the key areas of research that is still ongoing is really this ability to produce AI solutions where you can not only get the answer, but you can also understand why it got to that answer. And that's that is a problem that really needs to be addressed in order for AI to have the impact that it could have. We're just kind of at this infant stage with it, where we're using it, we don't understand why it does what it does all the time, and solving that problem will mean that we're able to better utilize it in situations where the consequences of a bad decision are catastrophic. So
yeah, John, a good place to put those guardrails might be in hardware because it's immutable.
Right.
Good point. So I did have one question, which for you guys, I kind of want to go maybe in a different order this time, just to try to solicit maybe some good responses to you in this question. So in your mind, given all these different things, given the fact that, hey, we got to go protect AI algorithms, we know that there's going to be a challenging supply chain to try to control. Given these things come from many different places, and when do you actually end in terms of the supply chain, right? It just keeps going and going and going, and at some point you're going to have some sort of foreign supply chain that gets into the mix. How do you go about creating a secure edge computing solution then in this type of environment? What can you do? Maybe think about first in terms of how you go about architecting a secure solution, and then maybe go a little bit further in terms of some areas where one would focus their attention on to ensure you have at the end of the day, a good edge compute solution that will at least have a good fighting chance, right, against some of these threats. So I wanted to first start with Will, since he was always last, in terms of what he thinks about that. So go ahead.
It's been the story of my life. My last name starts with Z, so I'm usually last. Yeah, where do you focus? For example, with supply chain, where are you going to focus? And I think whether you're talking about supply chain or you're talking about hardware security, cybersecurity, one of the biggest gaps is understanding the threat. And MITRE's done a lot of work on this. There's the Sparta. If you're looking at satellites, those things are really important. If you're talking about supply chain, I think if you're trying to look from an adversary perspective, you probably want to protect things that are closest to where the design is manifesting. If you're trying to go after, a mining operation someplace that, those materials, we're not talking necessarily about electronics, it's very hard to predict where that stuff is going to end up. And with electronics, you might have that as well too. Blind buys are really important. It's hard to target things when you don't know the materials that are going into those things. But at some point, the thing's getting assembled somewhere. The thing is doing its learning somewhere. It's got a data set. It's, you have things that are very close to the designers, very close to the systems engineers. And that's where it seems like you'd really want to have a lot more protections either through obfuscation, supply chain, as I said, blind buys, or other things in order to try to protect yourself from people being able to specifically target your system and also target it in a way that is going to be timely and useful to them.
Yep, absolutely agree. So, Wayne, over to you next.
Okay, yeah, so this is where I put in my selfish plug for ME Commons, right? Because I think that's what we're trying to do, right? We're trying to create not only, you know, I agree with Will, right? Part of protecting the AI models might reside in creating secure hardware platforms, right? That we can couple, you know, with those AI models. And so, you know, one of the things that we're looking at within ME Commons is, you know, a lot of the AI computation is being done on GPU platforms, right? So we have an effort where we're looking at, you know, taking that GPU and coupling it with a root of security, right? So again, putting hedges around the GPU, right? Or it could be something else, right? But putting hedges around it so that we can provide some additional layered protections, right? And being able to do that with the idea that we're going to create this capability onshore, so that, you know, trying to minimize you know, adversary or foreign exposure, right? So I think that's kind of the goal of ME Commons and the Secure Edge portfolio, is to try to figure out how we can create these secure edge solutions, you know, more quickly, I think. But again, it's a really challenging problem.
Yeah, and I think to your point, I think it's challenging because you're adding security, which may limit the performance, so to speak, of some of these things. So like, how do you make that trade, right? Between the two of them. It's likely the challenge that you have in front of you to decide how much uh, you know so to speak, oversight of the security that's running, that you need in terms of controlling interfaces, controlling other aspects of boot, for instance, on the GPU.
Mhm.
So that's just, I'm just curious, you know, if you're wrestling with some of those things.
Yeah, absolutely. I think there's a lot of performance trade-offs and hits in certain areas that we might take. You know, looking at secure boot, or you know, running during encrypting during runtime. You know, a lot of the things I think that's critical to succeeding in this area is really leveraging what commercial has done, right, within the AI space, and trying to sort of piggyback on top of that, right, so that we're not sort of reinventing the wheel, right? Because I think there's a lot of goodness that can be that we can leverage, right, especially from the government side.
Yeah, absolutely. And lastly, John.
Yeah, you know, I think, you know, I heard someone once, you know, ask the question, you know, what is the number of electronic devices purchased by the defense industry best approximated by? And the answer was the number zero. Um, right? We are a tiny volume of the electronics industry, you know, compared to commercial applications, which is, you know, 180 degrees from where it was 40, 50 years ago, right? You know, and to that extent, you know, highlighting what Will said, you know, the reality is the number of Intel CPUs or memory chips or FPGAs that, you know, somebody in the defense industry buys is, you know, pretty minuscule. So, you know, anybody who's going to really target that supply chain looking for a specific effect, you know, downstream, you know, that's a big thing to go after to get that smaller thing. So, you know, the closer you are to the application, we agree that the more important it is that you know, you do the right things to cover yourself. And you know, the other thing I think that you know, people think about the supply chain for semiconductors in particular. You know, they're very focused on the wafer fabrication aspect of it. That's just one piece of it. You know, that wafer gets fabricated, it goes somewhere else for test. It goes somewhere else to get cut up into individual die. It goes yet somewhere else to get packaged. And then, you know, those packaged parts likely go somewhere else to get tested. And, those are often completely different countries. A chip, by the time you've got it, it's got more frequent flyer miles than some of our colleagues. Right? So that's a huge problem, and as we talk about onshoring various capabilities, we really have to look at that entire chain. And that can help us, especially with some high value kind of components that maybe are present a greater risk to our system. I think the other side of it too is that you look at the security solutions that exist within the commercial devices, and they're addressing a completely different threat model than the edge. If you think about the typical threat model for commercial semiconductors, it's the data center where the external threat is an over the network adversary, or a co-tenant on a cloud server. So you can have different VMs running on a cloud server, and you may have your application running one VM, somebody in another VM can be running and taking advantage of side channel attacks to exfiltrate information or change behaviors, right? And there's lots of examples of that in academic press, right? Generally speaking, some of those threat models don't exist at all in defense applications and in typical edge applications, but rather the physical, which doesn't exist in those commercial applications, becomes much more important. So those opportunities that may be introduced in the supply chain have to be considered, right? And ultimately the design risk, how we mitigate those issues, because we're all working with those commercial parts at the end of the day, right? So we know their capabilities, we know their limitations, and then at the system level, we have to design that system to achieve the level of security that our applications demand.
Yeah, that's a great point. Your data center example is kind of what hits home to me. Is sometimes those sort of solutions aren't good for the edge, and you want to be able to disable them. And so we've run into those type of issues, right? Where how do we disable something that's already commercially available, just because it's in a different context and different threat model, right? That it's going after. So that's a great point. Just curious if you guys have any go backs on that question, because I think that was a great set of discussion points. But if you guys don't, I wanted to kind of move on to the last question before we get to the Q&A. I want to give folks some time to send in some questions. But lastly, what are you specifically working on, or currently working on, or have worked on in the past that you feel like have addressed this sort of issue with AI algorithms on the edge? And I'll give Will again the mic.
Okay. Yeah. I mean, working in the anti-tamper community, that community has a lot of knowledge, and it's not just techniques and designs and things like that. It's just the working knowledge you get from experience in working in that area. They tend to have a pretty sophisticated threat model, and again, I think that's really important to have that when you have people who are going to have physical access to your device. That's a really challenging environment. The thing I'm working on now, digital assurance for high consequence systems, is more about making trade-offs against different. So you have a threat model, but making trade-offs between cybersecurity vulnerabilities, hardware security vulnerabilities, and other things in the system. There's cost, schedule, and performance. I think sometimes in the security community, we tend to be focused very, very much on security. The people who are actually building the systems are focused, also have security concerns, but they also have cost, schedule, and performance and other things in the system that they have to worry about. And so, I think that it's all of these things kind of have to be put together in a rigorous model. That doesn't necessarily mean it's quantitative. A lot of times, I think these decisions are qualitative decisions that you have to make based on SME judgment. And so that kind of gets me back to where I started. I think there's a real need for training. Maybe probably starts with awareness, but then training and experience with people working with security in designing systems, because it's essentially a systems engineering discipline. That's, the DoD has adopted SSE. The National Nuclear Security Administration is going that direction now too. They're in consultations with the people who wrote those standards many years ago. Mark Winstead, Ron Ross, those folks are consulting with NSA now in order to incorporate that into how they're building systems. But you're not going to get, so if you have the ability to do trade-offs against security and things like that, that's good, but you're not going to get the result without a lot of experience. And that starts with training and getting people used to integrating these types of things into these systems, because in the anti-tamper community, when people were talking about building anti-tamper solutions for weapon systems, these were people who had lots of experience in designing these things into weapon systems. And also, when you're talking about commercial solutions, they have experience using those chips, turning things off, turning things on, using the security features that are available in those commercial devices, and then understanding the gap between where those devices are and where we need to be for a defense solution. And those engineers were key in elevating the security of those microelectronics devices using other techniques. Whether you're combining them in different ways, people talk about packaging them in different ways. All of that experience fed into what I think was a pretty robust set of solutions for anti-tamper, and I think that contributes in this area as well too.
Yeah, thank you for that. And over to you, Wayne.
Yes, I'll echo. I think Will did a great job of summarizing and capturing that. I think within sort of microelectronics commons, within our portfolio, we're trying to move beyond just swap, right? Everyone thinks of how do I reduce size, weight, power, and we add the S on, right? So we want all of our performers to think about how do we start integrating security into the design, right? As opposed to thinking about it as an afterthought, right? So we encourage all of our projects and our PIs to think about what the threat models look like. And a big part of the success criteria within the secure edge IoT area is thinking about designing to address holistic security, right? So it's not just thinking about protecting against side channel, but it's thinking about cyber protections. It's thinking about kind of the full life cycle of a piece of hardware, right? So I think within ME Commons, we're trying to push the needle on how we perceive security from a holistic point of view, and then have that translate to a lot of these AI and emerging platforms that you're going to see out in the field, right, in the next 5-10 years and beyond. So
Excellent. Yeah, I'm actually very stoked about ME Commons and all the good work that's happening there, and really looking forward to some of these innovative solutions, right, to that holistic problem. So yeah, lastly and not least, John, on this topic, and then we'll switch over to Q&A.
Sure, yeah. Well, so, I think one of the challenges is getting solutions that meet today's needs into the hands of the users who need them, meeting their craving for, state-of-the-art commercial capabilities in terms of processing, performance, memory capacity, et cetera, so they can deliver the best possible capability to the warfighter, right? But at the same time, getting the security it's needed. It does nobody any good if it's 5 or 10 years too late for the end application, right? And so how do you leverage those capabilities that you can get from commercial solutions and realize platforms that are composable and modular and allow you to tailor the solution to meet the need, balancing security with, things like boot time, for example. A commercial server might take, several minutes to boot up, right? But have a daily application that needs to be, live and running 10 seconds after you turn it on. And there's definitely in the security space a trade-off to get to, that kind of fast boot capability versus the security of a commercially relevant processing solution. And then within the lifetime of the system, how do you provide evolutionary capabilities to further improve the security as your understanding of the threat model evolves over time? Because certainly, what the threat model is today is going to change tomorrow as new RE capabilities, new semiconductor manufacturing tools come online, et cetera, right? There's always a better hammer, a better screwdriver, if you will, that's available next year as opposed to this year. And so you got to have a roadmap that goes along with these products so that you can, continue to provide, an ever increasing security posture to your customers and to their systems year over year.
Okay, great. Thank you, guys. So that kind of concludes our final panel session, and just kind of looking at the Q&As that we've got coming in. We got some questions here. So the first one I was going to ask, this is specifically for Dr. Chairman here. So are you looking at provenance and trace down to the IC level, like processors and memories, to enable full attestation from cradle to grave?
So that's something that we haven't looked at, in the sort of the first round of our ME Commons projects, but it's something that we're definitely interested in as we move into, the next call for projects, which, should be happening later this year. So it's definitely something that we want to be able to pay attention to. And if there's solutions to do that, then we would be, very open to that. Over.
All right, thank you so much for that. So are there any known, this is a question for anyone on the panel to answer. Are there any known legal implications or caveats to enacting blind buys in order to protect prospective technologies for forward DoD qualifications?
That's a great question. I know people do blind buys. I don't know what the legal implications are and what kind of hoops they have to jump through to do that.
Yeah, I'm not aware of any.
Nor am I.
Okay. Next question. Does embedding security into these systems necessarily reduce their performance?
Just to start, I think it depends upon how performance is measured. There's always a cost function, right? And it's, size, weight, power, choose to, right? Or, those sorts of, platitudes that we throw around when we talk about the cost functions. So at the end of the day, usually it's a question of, I have a capability and I need, a certain amount of, of processing capability or other capability in order to realize that solution. I either do or I don't. Is usually kind of how you evaluate that at the end of the day. So I don't think of these things as being a sliding scale that my tank is 10% less tanky because the performance is limited by 10% by my security solution. Right? It's gonna do the job it was designed to do if we're successful in delivering the capability with the security that's needed, and that's just another set of requirements at the end of the day.
Yeah, I'd say it's better to take that hit up front, right? You know, of course, like John said, it's going to cost something, right? But it's better for us to take that hit up front and understand what that cost is, as opposed to, hey, we go through the entire development cycle, we've got our whatever, our product, our widget, and then we realize, okay, we're going to put security in after the fact, right? I think that's going to cost a lot more from a number of different factors. So yeah, it's going to take a hit, but you know, it's needed. So
Yeah, I mean, you might take a hit with, you know, if you got to decrypt all your software before you can run it, it takes time. Might take layout space too, depending on how you implement that. We've actually seen people use formal methods though in the design process, and when they're using formal methods to verify their software, they actually end up finding less bugs later on, and they actually end up getting a quicker design time through security. So sometimes the discipline you add by doing these types of things, we talked about the crossover between reliability and security. You know, what caused the problem in your system? Well, if you're doing this type of thinking and trying to understand and model the different states your system can be in and roll some of those things out, sometimes you can get a performance boost.
Yeah, that's a great point. So next question, with so many intermediaries handling wafers on the hardware side versus firmware versus software and IP protections, things like that, how can all these factors be brought together for asset protection, especially with added threats of AI-assisted algorithms, including reverse engineering, things like that?
So again, I'm less concerned about you know, wafer handling. There's an awful lot of work that goes in on the commercial side. I mean, to verify that you know those those things are being rendered as designed.
Yeah, you're talking about quantifiable assurance, right?
Yeah,
Factories, they keep track of everything.
They do. It's not that you couldn't get in there and do something. I used to work in a fab. It's not impossible, but gee, it's hard. I'm more worried, and it's a provenance issue. Much more worried at the design side. Again, as I stated earlier, not necessarily. I mean, there's malicious things you could do with design, but there's plenty of things you can do just with a bad design or something you don't realize, where later on an adversary is able to understand your design. Usually the reverse engineer understands it better than you did, and they're able to find a way to subvert the system. So I'm more concerned about the logic and the thought that goes into putting a system together than the wafers. Other things in the supply chain, yeah, there are other things in the supply chain I think that are easier to subvert. Wafers and built chips, that's pretty tough.
Yeah, and you know, I think that you know, verification is one of the key areas that helps a lot with that, and really the level of verification, the attention to detail that goes into that process, especially in FPGA-based systems, you know, can sometimes be a little bit lacking just because there's maybe you know, an attitude or a thought process that says, well, you know, I can always fix it later because it's reprogrammable, right? Whereas in the ASIC world, where a lot of my career I've lived, right, you know, I mean, if you've got a bug, you know, and you got to go spin the chip, you know, you missed your market window. You know, it's an economic disaster. You know, that can put a company out of business, frankly. You know, and so the kinds of techniques that you use, you know, and to get the sign off in an ASIC, you know, are typically not used in FPGA-based designs that are dominant in defense. So, you know, I think that's an opportunity to really look and see, you know, where we can really up the game across the entire DIB in terms of the verification of the designs, make sure that we, you know, don't have latent issues that can be exploited at a later date.
yeah, not much to add from John and Will, but you know, traceability as much as possible is important. And I think at some point we'll rely on additional AT hooks that we can put into the design, right, to kind of make it more robust. So
Yeah. Well, and having been in the IP business for a long time too, I think one of the things you have to recognize is, modern chips are, often have a high percentage of content from a variety of different suppliers, and the provenance of that, maybe is not always clear. Especially, if you're using, say, an SoC FPGA, for example, right, where, there's a whole Swiss Army's knife of functionality built into it. Where did all that IP come from? And I'm not saying that there's anything maliciously intentionally put in there, but, what about the potential for a latent defect that, winds up being, an area of concern. Right, and that's definitely one of the issues that you have to think about, and even more so if you're purchasing IP to put into the device yourself, because of course the developer of the FPGA, the SoC, will have actually put a lot of effort into verifying it and making sure it's pretty rock solid. But when you go to that third party um, for that additional IP, which maybe even as the FPGA vendor itself, through a foreign subsidiary that produces the IP, and you need to understand that, and either accept the risk or mitigate it. So those are important considerations as well.
Yep, absolutely, yeah. And so I just want to let you guys know there's an excellent conversation. I appreciate you guys' time on this panel, and I think it was really hit at the heart of the not only framing the challenge, but also some ideas for our audience in terms of things that they should kind of think about and do to try to address this problem. It's gonna be holistic, like you guys mentioned multiple times, and it's gonna take like a multidisciplinary team to really go after and to really go after a lot of these different things. So with that, I'm going to close out the session, and I appreciate you guys' time and with the panel today. And I will hand that over to NDIA right now.
Hey,
Thank you.
thanks, Tony, and thanks to the panelists for a great session. That was thought-provoking and scary and hopeful all simultaneously. So I appreciate that. Very, very realistic, but also it's not hopeless. There's a lot of good work going on, and I guess we all, government and industry together, have to make sure this is prioritized both in requirements and in programs and in funding. And I think you guys laid that out very, very well for us. So I really appreciate that. So I want to thank everyone for attending and talk to you a little bit about other things that NDIA and ETI are up to. ETI has some great upcoming events coming up in July. Our next Tech 101 webinar, which is on wearable technologies, is on July 23rd, 2025. We've got a couple of events coming up also in the month. One is a webinar called Becoming a Technology Apostle, how to successfully discover, nurture, and implement emerging technologies. We're doing that in partnership with Parallax Advanced Research. That's on July 18th. And we're having an in-person short course on engaging private capital in defense industry, tactics and trends. That's on July 22nd. Be on the lookout on NDIA's calendar of events page for more information on all these events. I want to talk also about the NDIA Emerging Technologies Conference, which is going to be held August 27th through 29th at the Washington, D.C. Convention Center. Confirmed keynote speakers include Undersecretary for Defense for Research and Engineering Emil Michael, Undersecretary for Acquisition and Sustainment Michael Duffy, and the Vice Chair of the Joint Chiefs of Staff, Admiral Christopher Grady. Please visit ndiatechexpo.org or scan the QR code in the corner for more information and to register and to find out about all the breakout sessions and panels that are going to be happening at that event. At the event, we're having a DTIC classified reading room where cleared personnel can review COCOM integrated priority lists. The deadline for registering for access to that is coming up very quickly, Friday, July 18th. The conferences will also include classified sessions with speakers representing the COCOMs, OSD, and other services and defense agencies. Registration to attend these classified sessions is also on the conference website. Conference is going to include one-on-one speed dating sessions with participating government and private organizations. More details on those speed dating sessions and how to sign up is to come. And then I also wanted to mention that we're going to be holding a hackathon at the conference. Registration is open now, ndiatechexpo.org/hackathon. Thanks again to Tony and the panelists, and thanks everyone for joining us today.